Welcome to Thinking Deeply About Primary Education, the podcast that makes time and space to think about pedagogy, teaching and learning, professional development, anything of interest to time-poor, enthusiasm-rich primary teachers. Now, this week is the annual From My Mum's Kitchen episode, but luckily, most of the chat will be from Stuart Welsh because this is a special, sort of almost most people on half-term break episode, but also the launch of TDAPE Online Conference. And the TDAPE Online Conference is going to run for the next 12 months. Tickets on sale for the next 6 months. And we're going to raise money for Velindre, especially for those people who think, oh, there's a TDAPE conference in London, but I can't make it, or TDAPE conferences across the UK, but I live overseas. This is for you because we've got really high quality sessions, just like we would in a live conference, but they're going to be available from a especially dedicated website. And you buy a ticket via Eventbrite, you'll get a key to unlock the sessions. We raise money for Velindre, and everyone gets access to really high quality PD. So Stuart's episode today is going to be an example of the high quality PD available. All you're going to do is follow the link in the description, and it will take you to the Eventbrite, and then it'll give you all the information from there. And like I say, we're going to be recycling the talks, so the more talks will be added on a regular basis over the next 6 months. And if you're listening and you haven't yet submitted the talk that you said you might have, well, now is the time to do so because we've got a stellar cast already and we're going to keep improving that over time. So without further ado, it's over to Stuart and let's help us raise as much money as possible for the Velindre Cancer Centre.
Hi there, my name is Stuart Welsh and welcome to this session, Beyond the Right Answer, where we'll be looking at some practical ways you can use in the classroom to try and develop mathematical thinking. So often when I'm working with schools and teachers, there's a lot of great questioning going on, but when do we tip from surface level questioning into deeper questioning? What tools do we have at our disposal? What strategies and techniques can we employ? And that's really the main aim of this session. So if you are interested in getting in touch with me, you can see my email address on the screen there, stuart@alta-education.com. Always happy to chat about all things mathematical, but for just now, I think we should just get underway. So first and foremost, I did say that great teachers ask great questions, and effective questioning is obviously a very powerful tool in our toolkit, but how do we use it to go beyond the right answer and actually encourage students to behave a little bit more mathematically? And when I say behave a little bit more mathematically, I'm wanting students to think more deeply about the structures and the concepts, to be able to explain their reasoning and not just give us a correct answer. And then, of course, to be able to start to form and see those connections that exist all the way through mathematics. So really, I suppose the point here is that we want to try and ask questions that focus on thinking more than just getting the right answers. Even just as simply as instead of asking, what is the answer to this? We ask, how do you get the answer to this? And even that little shift changes the thinking that's going on by the students and changes the response. So we're going to focus on thinking. We're going to try and find ways of making their thinking visible, whether that's using concrete or pictorial representations, or just any other way that they manage to sort of communicate their thought process. We want to try and, as I say, go beyond just that right answer. So straight up here, I've got a little image prompt for you on the screen, and all I want you to do is have a little look at this and think, what might the question be? So what could you perhaps ask your students? Now, it's important as we go all the way through this session that you think about your own context, because I don't know the stage or age of students that you work with, but what is really clear to me is that encouraging students to think deeply, the strategies that we're going to explore in this session transfer all the way through that maths journey. So from the very youngest students all the way through to those nearing the end of their formal education, the sort of principles and strategies that we're going to talk about today are useful all the way along that journey. So you're looking at these and you might be thinking, questions I might ask my students could be, how many apples? Obviously a good one if we're working with younger students. Or, as you're further up through the curriculum, you might be asking, if this was a pattern, what might come next? Obviously, that explores quite interesting conversations around, does the pattern continue vertically down the page, or do we actually work out to the right and left? But questions for me, building on that, how many are there, is actually just that variation, and just say, how do you know there are 5? And then really just encourage them to focus on that skill of counting. So how do you actually know that this is 5? And you might get that sort of one-to-one kind of counting, or you might see students saying, well, I can see 3 on the bottom row and 2 on the top, and that kind of comes to 5. So just interesting ways of this kind of structure of how the count might be achieved. And again, you can ask them, how did you count them? So a lot of people will see horizontal rows here. Some people might just look and see 5, and some other people quite often see a kind of diagonal pairing of 2 with 1 extra. So lots of ways of sort of talking here about how we might come to that total count. But then sort of interesting to just explore that, okay, you've got your answer and you've done it your way, but how might somebody else have done it? Is there a different way to go about this? And so even from this very simple 5-apple prompt, we can go much further than just saying how many are here, and we can sort of dig below the surface and really see if we can get students to think a bit more deeply, but also to communicate their thinking with us. So a nice straightforward example there. Let's move a little bit further up through that maths journey to order of operations. So a kind of classic here, 3 + 4 times 5. Now, whether or not you work on this type of mathematics with students, you will have seen this type of calculation, and there's obviously a classic mistake to be made here, and that is students working from left to right, literally as this comes, because as we know, multiplication has a higher priority, a higher order of operations than addition, and should be done first. But a lot of students just learn that as a rule with no kind of understanding to sort of pin it to. And so one question here that you might be asking is, what is the correct answer? But maybe more interestingly, what is the common wrong answer? And what have people done to get there? But my question for you, which is slightly different, and by all means feel free to sort of pause and take a moment to try and do this, is actually, can you draw this calculation using some sort of simple model, some sort of pictorial representation, maybe an area model or some sort of array? So I'll give you a few seconds, whether you're going to be drawing that out, or you might be thinking about how would I kind of visualize this sort of expression here, and what might my students do if I asked them to draw a calculation like this. And so, having thought about that, I'm going to show you how I might represent this expression here with counters. So first of all, I would show 3. And then what we're doing is we're adding to that. So we're bringing more into the system. And what we're bringing into the system is 4 lots of 5. So there's 1 lot of 5, another lot of 5, another lot of 5, and finally a fourth lot of 5 there. I've been very specific. You can see that sort of array there. You can also see this idea of sort of almost unitizing the 5s and saying now we're counting in groups of 5s, and how many have we got? We've got 4 of them, because 4 times 5 is 5 being multiplied by 4. And what we can see here is we count these counters, there's no way that we are not going to see the correct answer here of 23. The commonly occurring wrong answer here from addition first would be 35, but we can kind of quickly dispel that and say, well, that's not 35 counters represented here. So I think it's quite interesting just to play around with this idea of visualizing like this, and seeing if we can push the students to form a kind of different representation in their minds. Now we're going to go a step up again, and just play around with this a bit further and ask if we can find any values. So basically replacing the 3 and the 4 and the 5 with anything we want, we're actually doing the wrong thing. So adding first instead of multiplying does actually give you the same answer as if we were to have multiplied first. So again, I'm going to leave this with you just for a few seconds. Feel free to pause, take a moment, and actually try and come up with some numbers, some values to replace the 3, 4, and the 5 there, and see if we can actually find sort of some special cases where addition first does give the same answer as multiplication first. Now, I hope you had a chance just to think about that. This is definitely something that you could do with students, and I think students find it quite interesting just to sort of play around with this and see if they can kind of break the rule or find a kind of hack for the system. I'm going to show you what some of the responses might look like. Here's just an example here where all we need to actually do is sort of keep the 3 and the 4, but replace the 5 with a 1. And so you can see there that on the left-hand side, doing the multiplication first gives us 3 plus 4 lots of 1, which is 4, so 7. Or we've got the bracket forcing the addition there, and gives us 7 times 1, 7 lots of 1, giving us 7. So there's one example. Here's another one in here. So actually, I sort of change that first number there, and that still holds true. And there's another one. And, already there's some sort of patterns forming here. There's sort of a bit of variation, but there's also things being held constant here to make this true. So we can start to talk to the students about, what is it that we notice here that's kind of making this work? And then at some point they'll say to you, well, it's the multiplication by 1 at the end there. And then you can dig in and say, well, does that mean we can have any numbers at the beginning? So the 3 and the 4 could be, anything, but as long as we have times 1, and we can explore that. But that's not the only solutions you might get. You might see some students eventually come back with this. So slightly different because we've obviously introduced a 0 at the front. Still got that 1 on at the tail end. So what is it that's really making this work? Well, let's explore that further. Change the 1 at the tail end to 2, but keeping a 0 at the beginning. This kind of still holds. So it's starting to look a little bit like that end number, which was a 5 originally. If you replace that with a 1, it seems to satisfy our criteria. But also separately, if the first number, which was originally a 3, gets replaced with a 0, that also seems to hold. So we could play around with this and see if that students can sort of convince themselves that this is true. But if we really want to convince ourselves that this is true, then there is an equation that we could build here. The 3, 4, and 5 replaced with the letters A, B, and C. And what we're trying to do is find values of A, B, and C that sort of solve this equation, that make this equality statement true. And so, again, I'm going to give you just a few seconds to look at that, whether algebra is your sort of something you do day in, day out, or whether it's something you've not sort of played around with for a little while. Maybe you can remember like the distributive law to expand these things and simplifying equations. Those would be the steps. So can you solve this to find values of A, B, C that make this true? And so, having had a few moments to think about it, what would happen here is, as I say, distributive law on the right-hand side would expand that bracket across. And then we've got a positive BC on both sides of this equation. So we can subtract BC from both sides of the equation. And we're left with this. Now, this might not look like a solution, but it kind of does open up the doorways for us here, because now through sort of inspection more than anything else, or sort of logical deduction, we know that there are only, 2 possible ways of making this statement true. Either A must be 0. If that's the case, then 0 equals 0, and we're using that important property of multiplying by 0 gives us 0. Or the other way to make this true is that C would have to be 1, and then we would get A equals A. So what's really interesting here, I think, is that from very humble beginnings, a straightforward order of operations question, we've gone into a kind of pseudo proof here and exposed children to sort of some algebra, and a visual representation that all kind of ties up and goes hand in hand. So that brings us to the end of our kind of questioning section, and probably to the end of the hard maths. And so we'll go kind of all over the curriculum here, just to try and highlight the different strategies that we're talking about. But if we move on to this idea of purposeful prompts, then the type of behaviours that I'm hoping that we'll see from students will be, deepening their understanding and starting to see them make those connections, and quite importantly, just be kind of curious and almost playful. We want them to investigate patterns, and we want them to try and identify different strategies and then justify their choices and the decisions that they've made. And so what might a purposeful prompt look like? Well, here's one, I think quite a nice sort of simple prompt here, which goes, in my mind anyway, from very, very early mathematical experiences all the way through that students' maths journey all the way up to the top end of sort of secondary schooling. And so I'm not going to give you just 3 stills. We'll have these little characters just now. And again, put yourself in your context. So think about the students that you teach just now, and what question might you ask them based on this visual image, this visual prompt. And I imagine some people are maybe thinking, how many legs is often one, how many eyes, those things start to appear. And then we need to decide, are we counting the animal legs as well as the chair legs, etc. So we've got all sorts of things. Now, they're actually all different heights. And so, you could, in theory, model this live if you had the items, and you can maybe put them in order of height. And here you could maybe introduce words like middle and left and right, and all sorts of kind of early positional sort of understanding. But for me, I think I would be looking at asking something like this, maybe, just sort of thinking, they don't have to sit where they're sitting. What if we swap their seats around? So how many different arrangements are possible? And what I really like about this prompt is that almost every student should be able to access it at some level. I don't know if they'll all be equally skilled in terms of the structured approach, because that's something that we want to develop with them. We want them to be organised and ordered in their thinking, and so maybe they'll introduce letter labels for these things, which in itself is a great sort of step forward, and then maybe they'll start to build a sort of list of combinations, and will they be structured in the way they approach that list? Maybe not, but maybe they will, and we can talk about that. A key thing here is always how many arrangements are possible, and how do you know you've found them all, which is sometimes very difficult for students to actually put words to. So they might feel very confident they found them all, but they do struggle to find the language to then communicate the reason why they have them all. And that's something that we can work on with them, and this type of sort of conversation and prompting helps with that. A slightly different prompt that you might ask here: if the white cat must sit to the left of the brown bear, how does that change the number of possible? So we've added a constraint in here, which I think is really interesting. There's maybe a bit of a discussion around what do we mean by left? Is it the bear's left or our left? And get those kind of, define the problem clearly so we all know what we're tackling, and then sort of play around with this slightly constrained version of the original problem. And then another one that might come out here, is if I only had 2 snacks, how many different pairs of pets could get a snack? And, we're looking here at essentially permutations and combinations, which is, really quite sophisticated, high-end sort of top-end mathematics, but all started off from a very, very basic kind of prompt here. And we'll come back to these 3 characters right at the end of this session and see them in a slightly different light. But for just now, let's move on. We'll have a little look at manipulatives and visual models. And the reason that I've included this in here, because we're talking about going beyond the right answer and that deeper mathematical thinking. The manipulatives and visuals certainly allow us to explore concepts. And what we want to try and do is use visual models and manipulatives in a way that they're like a progression towards abstract, so that we're making sure we've got a coherence throughout those representations. Sometimes it's very tempting to use a physical manipulative or a pictorial representation, because we think it helps build conceptual understanding. But if the abstract method that we then present to the students, or that they meet further down the line, doesn't actually align with what we've been building, then that just brings confusion more than anything else. So important that the models and representations are there to sort of scaffold and support the abstract method that we then move on to. And I think running through all of that is the consistency of language, and you maybe sort of pick up on that as we go through the next example. I think that we're trying to build understanding throughout all of this, and if showing students a representation that helps kind of clarify or expose a structure or a concept that purely viewing an abstract representation wouldn't do, then I think it's a very powerful tool for us. And so what we want students to do is just kind of play around with representations a little bit. We should sort of be a bit playful as teachers as well, I wonder what happens if we try this. Could we do this? But then obviously steering it towards the modelling that we want to use. Like I said, linking the manipulatives up through language and through the formal notation. There's nothing wrong at all in my mind with having a manipulative, but also having an abstract representation going side by side to really sort of show those connections. These are the prompts that start to help students deepen their understanding and connecting up the concepts across topics. In fact, we even sort of explored the concept of order of operations earlier when we looked at those counters and that kind of array structure. So I'm going to give you a question here. Again, maybe some of you are thinking, well, I don't do this work with the students I teach, the group of students I teach, but the underlying idea is how are we going to use a manipulative, whether it's concrete or whether we use a pictorial representation to help introduce this before we move to the abstract. And when I say abstract, I'm really meaning kind of the symbols and the notation that we use mathematically, because these really are kind of arbitrary sort of symbols and markings on the page. They do have meaning underneath them, and for us, we look at this and we have the knowledge to connect these representations to their meaning, but a lot of students don't, and for them these are just kind of random markings on a page, and it becomes very sort of tempting for students just to then try and latch on to sort of shortcuts and tricks, and if I see something like this, then the answer must always be that. And here, a classic mistake is that idea that two negatives make a positive. A lot of students sort of seem to believe that, and they've probably been told that in the right kind of sense, well-intentioned, but this doesn't hold here. Two negatives don't make a positive. The answer to this is not +8. So my challenge to you, just for a few moments, is to think about how you might introduce this using concrete materials and or pictorial representations before you move to this kind of purely abstract. So having a think about this, even if you don't teach this to the group that you work with, negative numbers, how might we sort of bring this to life and build that kind of conceptual understanding underneath it? Now, when I talk with teachers, quite often we get a temperature coming up here as a sort of kind of idea to embed the concept, or debt. Sometimes kind of money and debt is perhaps useful. Although adding negative money feels like, I don't know, I'm not sure how I would fully kind of explain that. Or kind of altitude is sometimes good, maybe sea level and below sea level. So a lot of people say to me this is the sort of conversations they have, but I would then sort of push back and say, well, how exactly would you discuss this very calculation here? If a student was presented with this, how would your model or your sort of metaphor handle this? And then other teachers, and you may be looking at this and you're probably thinking number line. Number line is often mentioned here, and I would again, just reflect back and say, well, how exactly would you tackle this calculation given here using a number line? And some of you are maybe thinking counters as well. Counters are really powerful, I think, for sort of negative numbers. And so I'm going to show you a couple of things. We're not saying you must do this, just saying some things that work for me when I'm working on negative numbers. So we take our calculation, -3 + 5. We have to introduce like two-sided counter here. So if you haven't seen these kind of counters, then yellow is commonly taken to represent +1, and red is commonly understood to represent -1. And really, before you go anywhere with these counters, the first thing we need to communicate with the students is that when these two are brought together, the yellow and the red, the +1, the -1, they produce 0. The net result is 0. This is what's called a zero pair, and it's kind of fundamental to doing negative number work with these counters. So a yellow and a red together makes 0. They basically eliminate each other, kind of cancel each other out. So how would I introduce -3 + -5? Well, I'd say, one red counter represents -1. How might we represent -3? Here we are, 3 red counters. And of course, we're adding into this system here. But what we're adding is a -5, and how would we represent -5? Well, it'd have to be 5 red ones. And then what we're sort of looking at here is this idea of sort of aggregating these two values, a kind of bringing together. And I think it's actually powerful to do that kind of visually and just say, well, we had -3, we've got -5, and we're adding these two things together. We can see them coming together. Now, those reds have not changed colour. They are still red. We had some reds, we had some more reds, we brought them together, an even bigger pile of reds. Reds are negative. Answer to this is -8. There's no way that students are going to think this is +8 if you build it up from this level of understanding. No need for shortcuts, no need for tricks, no need for two negatives. Make it positive. Now, I mentioned number line, and my challenge is always, okay, number lines are powerful. How would you actually go about discussing this calculation? And you can do all possible variations of negative number work on a number line like this. When I'm teaching, I introduce the idea of the sort of additive inverse. I don't really talk about subtracting at all. I talk about replacing a subtraction with the addition of the opposite of what you've had. Now, that's a whole other session, a whole other conversation, but for our purposes of this session, I just wanted to model this here for you, because students may be able to place -3 on this number line. They'll plonk it somewhere to the left of 0. They're probably able to spot -5 and place it on the number line as well. Hopefully they place it even further away from 0 to the left than they did on -3. But what I think a lot of students don't appreciate is that these aren't just a point on a line. These have magnitude or value. And so what does -3 actually look like? Well, we saw 3 counters earlier, 3 red counters. We saw 5 red counters, and we can see that there was more. And we can also represent this in this kind of linear way. So that is actually a vector, isn't it, that represents -3. It's got magnitude, it's got direction. And so I'd say to students, okay, draw me -3. And yeah, you have to train them in this. Draw me -5. And we can see the two of them, and then we can have this conversation about -3 plus -5. What does that mean? And so, whereas with the counters, we're sort of bringing them both together, this idea of sort of aggregation, then here what we've got is a -3, and then we're going to add on to the end of it. We're going to add on to the end of it this -5, and we can see that this entire thing, that the totality now journeys all the way down to -8. I think this is quite a nice idea, to reinforce that representation. So the counters, we had that aggregation. Here we've got an augmentation, so -3, and the -5 has been bolted onto it. It was in place, we're bolting that on. But again, this is never going to be +8 if we build up this level of understanding. So, a slight aside there as we went into those models, but I've spent a lot of time trying to get students to understand negatives, and I've gone around all the houses, and for me, the counters and number lines like this now are by far and away where I've had the most success. Okay, pushing on then, after manipulatives, we're going to try and encourage some discussion, because again, these are the sort of traits, I think, that school mathematics can develop if we try purposefully to go beyond the right answer and ask these questions and create these scenarios where students are having opportunities to improve their reasoning and encourage their sort of discussion, their communication skills, being able to explain what they are thinking, but also being able to listen to others and hear what others are saying and reflect on that. To an extent that they become flexible in their own thinking and say, well, I had thought this would work, but now I'm wondering if this might not be always true. Absolutely fantastic mind space if we can get students into them. So one thing we can do is use kind of open-ended prompts to build that discussion, get students to build on each other's ideas and try and encourage them to find multiple solutions, not just one way to get there. I think we do have to battle against this idea that being good means that you get to the right answer first, because being good at maths is not about getting to the right answer first. I think correct answers are preferable, but explaining the journey, understanding the steps, and looking at different ways of getting to the same end point, really much more powerful than just quickly getting to the right answer. And so here's a task for you. You can play along if you've got a bit of paper and a pen. The first thing I want you to do is you probably make 5 little horizontal placeholders here on your page, because I want a set of 5 positive integers that meet all these criteria. Now, the first criteria is the mode is 3. Now, I don't know how hot your statistics are. I imagine you'll all know the mode in a set of numbers is the number that occurs most often. And so there's a few different ways of creating 5 where 3 is the number that occurs most often. So hopefully you've listed that out. And I'm sure somebody's got 5 3s, which would be absolutely fine. But as long as you've got more 3s in there than anything else, then that's going to work here. And this is the important bit. We're now adding a second criteria, or a second criterion to this list of criteria, where not only does the mode have to be 3, but now the median must be 5. And so we've sort of sharpened the constraint here. Now, this works really well in pairs if you get students to work together, because they'll debate and discuss how they want to adjust their first set to then match the second set. Now, the median is the number in the middle, as long as the list is in order. So get that set of 5 in order, and what we want to do is still have more 3s than anything else, but the middle number must be a 5. And then that's always good for students to have that discussion around it. But then we bring in another constraint, the mean. So you'll remember that the sum of the values divided by 5 in this case has to be 6, but the median still has to be 5 and the mode must be 3. So you can see that students will now have a bit of fun playing around with this, and hopefully you're still playing along as well. Have you got a set of 5 positive integers that satisfy all 3 of these? I hope so. The final one then, the range needs to be 8, and the range is the largest minus the smallest. And so what you might find you're doing now is you're adjusting, both ends of your set of 5, or maybe you've had to go back in and adjust something else as well to try and make sure that all 4 of these criteria are in place. The prompt here is kind of work together and compare your solutions as you go. Has everybody ended up with the same answer? Is there only one way to solve this? Which is always quite interesting. And also, have a conversation around which of those conditions there was the most restrictive. Which one did you really have to think about? Which one really focused it in? Maybe it was the last one, although I think the mean also requires a bit of kind of focus. And then, of course, are there any other solutions? And if you think you found them all, explain why there can't be any more. So this, I took this curricular example of kind of statistics, but you can absolutely use this with things like types of number, and I talk about odds and evens and primes and squares, and different areas of maths where there's a few factors that can kind of come together, and really we're sort of thrashing out definition, but we're also building it up in this sort of increasingly difficult sort of constraints scenario. Right, so let's move on to examples, non-examples and boundary cases, something so powerful when we want to not only sort of explore concepts, but really find the limit of a concept, building that deep understanding, testing those limitations, and then, refining our thinking around what a concept is, and if what we're talking about still fits the concept, and when does it not fit the concept. And so, we can really deepen understanding. We definitely want to be pushing students to justify. So you'll see in the examples that are following where we can really ask students to say, well, why does that one work? Why does that one not work? And by homing in on the threshold, then we can really get a tight definition of the concept that we're sort of studying. And then again, we can sort of try and encourage these really precise definitions by carefully steering the conditions. And so here's a sort of example here, and you can do this again yourselves. You can do this just now. First of all, we're just sort of building up the structure here. So write down some fractions that are greater than 1. And the constraint I've put on here is that we don't want any mixed numbers. So write down some fractions that are greater than 1, but we don't want any mixed numbers. So you can write down a few of these, 2 or 3 of those. I'm sure you've all got something written down. Now, what I want to see is some that are less than 1. And so students and anyone participating has to now think, what's the switch here? What's changing? We haven't gone super tight into the boundary here, but we're certainly looking for examples and non-examples. And then what about some that are equal to 1? So we've already built out a little set here that's starting to form the definition of fractions around or equal to 1. And then just have this conversation, and this is kind of a vague prompt, but we don't want to be too specific in the questioning because all sorts of interesting things come back from students, including misconceptions sometimes. And so if we ask quite an open question like, what do you notice? Then we might start to see that, there's a little misconception surfaces that we can then explore and we can discuss. But obviously, where we're sort of heading here in terms of numerator greater than denominator type thing. And some people will have some really interesting examples, and it's always worth chatting through those. So now we can build on this, and we can ask students, and again, you can do this, to write a fraction where the numerator is 1 more than the denominator. And they'll very quickly be able to come up with something there, and then we can follow that with this one. So a fraction where the denominator is 1 more than the numerator, just that subtle sort of switch around there. And then, again, quite an open sort of prompt about what sort of makes them different. And there you can really get a sense of, how students view fractions, the role of the numerator and the denominator. You can absolutely have a conversation about, smaller part sizes or more of those parts. Again, a nice open sort of prompt, but we're digging deeply here into the sort of definition of fractions around 1, but we can go further and push that understanding a little bit. This is an interesting prompt, and you don't have to do this just with fractions. I think that's the key thing here, is we want to just ask students to give some examples of a thing. So, I don't know, like a square, give another example of a square, and then give an example of something that's not a square, and then, give something that somebody might think is a square but isn't, type of thing. And so in this case, we're using fractions. And we don't really know what students are going to say here, but they can absolutely come up with some interesting things, and we can have a little conversation around those. And then I think where this gets really interesting is, exploring the thresholds. And so let's write fractions that are really close to 1. So maybe 2 fractions on either side of 1 is like kind of as close as you can get to 1. And, we might end up with things like 9/10 or 11/10, which would be great. But then the sort of push here is, can you refine those fractions, make them even closer to 1? And suddenly we see how we're pushing the boundary here, because 9/10 could become 99/100. That's closer to 1 than the last one was. But really, students have to have a deep understanding of fractions before they kind of can do that, and before they can have a conversation around that. And we just ask them, what are you changing to do this? What is it that has to happen? And they might just say, the numerator and denominators, just as they get bigger, as we add more powers of 10 to the denominator, for example, we can start to see we're talking about even smaller fractions every time. And 999 out of 1,000 is just 1,000th away from 1, whereas 9/10 was a 10th away from 1. Really rich, fun conversations to be had in there. Okay, quick look at comparison and sorting. Again, quite useful for visual stuff, but doesn't have to be. We can group types of numbers in here. And the prompt in this case would be, sort them into rectangles and not rectangles. But actually, the prompt could be nothing. And it could just be, group these shapes in any way that you see fit. And that's always quite interesting to listen to students try and sort of explain and justify why they grouped shapes or grouped elements, whatever it might be that you'd presented with them, into certain ways. So there's no real wrong answers here. But if we push for this idea of rectangleness, then that's why this is, because rectangles have got 4 sides, so that's every shape here. But no, rectangles need to have opposite sides or parallel, so that needs to be a thing. But does that still include A? So what else is going on? Well, we need to have right angles in there as well. And that's like B and E, but what's D doing? Well, just important to always try and show shapes in unfamiliar orientations. D kind of looks a bit like, I don't know, A maybe, if you think about it, but D is, of course, a rectangle in this case. So really rich conversation to be had by carefully choosing the kind of elements for the set that you provide. Here's another comparison and sorting task. You're more than welcome to sort of try and do this, but really, if you put yourselves in the shoes of your students and think about what would they be thinking here, sorting these numbers into sort of groups that to the nearest whole number, they round to 10, and those that don't. And so instead of just saying, here's a bunch of numbers, round them, what we're doing here is we're exploring this boundary again, what rounds to 10 and what doesn't. In fact, you could do the sort of the question that we did with the fractions here on this as well, and give me an example of a number that rounds to 10, one that doesn't, one that's really close, one that somebody might think rounds but doesn't round. So often the 10.5 comes in there. So a nice little activity, I think, here to just go beyond, as I say, the right answer and push a little bit more toward the understanding. And hopefully you're thinking, well, I might not do rounding to 10, but I can still see this idea of the boundaries and examples of things that are true, and then the non-examples, and then those things really close to the boundary of the concept, which is where the really interesting sort of conversation lies. Okay, so find all the ways. Doesn't just have to be done with dice like this, of course, but here's quite a nice little example where we can ask how many ways can we choose 2 dice here from the set to make a total of 7 dots. And then how can you be sure you found them all? So I don't know how many ways are there here. So the 1 and the 6 might work, the 2 and the 5 could work, the 3 and the 4 could work. And then we can maybe have a conversation around, does picking the 6 before the 1 or the 1 before the 6 mean it's a different one, or talk around that. How can you be sure you found them all? So good to then push those students to try and justify their answers. But I think what's interesting about this style of questioning is it opens up the next one, which is super, super powerful. So not only have we got a kind of open-ish task here, but it lends itself so nicely to this idea of what if not. Now you can see the words that are coloured in yellow here. So how many ways can we choose 2 dice to make a total of 7 dots? Well, it doesn't have to be 2 dice. It could be 3. It doesn't have to be total. It could be product, and it doesn't have to be 7 dots. It could easily be 10 or whatever. And so what we've got here is, once you find a nice kind of question and sort of open-ish prompt, then don't forget that you've got the ability to then tweak the parameters within that question and sort of move the goalposts a little bit, just to make this kind of a bit more interesting. So how many ways can we choose? I don't know, 3 dice to make a product of 24 or something like that. And suddenly that's much more exciting, this question, than just essentially sort of number bonds to sort of 7. And it takes us right back to these characters from the beginning, because although we had a sort of combination and permutation type question, it doesn't have to be 3 toys sitting on here. So what if we had 4? What if we had 5? How does that change the task, the challenge of the task? If there was 5 stools with 5 different animals, how many different ways of arranging them becomes much more interesting. And actually, as you do add more animals to this, you start to head towards the sort of students seeing the generalization of like factorial, which is the way to solve these types of problems. So only a couple of things to look at before we're finished. You've probably heard of this idea of always, sometimes, never true. So always true, sometimes true, never true. It helps students, develop their critical thinking. They have to analyze statements, really deeply, exploring sort of exceptions and justifying the reasoning. I think what's really good is it really sort of encourages misconceptions to surface, but throughout it, we're using that mathematical discussion to sort of push for reasoning. And so I'll go through these quite quickly, but you would ask the students, is this always true, sometimes true, or never true? And then have a conversation around this. Now, diagonal is a particularly sort of contentious thing, and so I'll leave that with you, whether you think a diagonal is always horizontal, sometimes horizontal, or never horizontal. And whatever your answer is, can you give an example of it, or explain why you've come to your answer? Another one here, 2 times the number is greater than 2 plus the number. Is that always true? Feels like it. Multiplication is quite a powerful thing, always makes things bigger, but maybe it depends on the number, so maybe it's sometimes true. Can you give an example of when it is true and when it isn't true? The sum of 2 even numbers is even. Is that always true? Sometimes we need to think about that, maybe give some examples. Perimeter of a shape greater than its area. So that's sometimes always or never true. If you think it's never true, then you have to try and come up with some way of justifying why it can never possibly be true. Is it always true? Maybe sometimes. And if it's sometimes, then sometimes is where the interesting conversation lies, because if it's sometimes true, then that's when we can say, well, give me an example of one that is, give me an example of one that isn't. Adding 2 numbers gives a greater result. Well, there's a good conversation to be had around those. Maybe takes us back to our -3 plus -5 earlier on. That might be a good one, bringing in the negatives. Multiply a number by a fraction gives a smaller result. Does it always? If it does, give me an example. If you can find a time when it doesn't, give me an example. And then dividing, giving a smaller result. Area of a square is equal to its perimeter. Is that ever true? Can you find an example where that's true? Can you find another example where that's true? So loads and loads of really interesting things to explore in there. Right, and I think we're moving towards the final one, this idea of hard and easy. So I think this matters because, getting students to generate hard and easy examples, it means every student can engage. They sort of set the difficulty level themselves. It gives access to all students. We've got this idea of sort of multiple entry points. There's access for all students here, and deeper understanding often kind of emerges as they sort of test and refine and kind of justify their thinking. What's important here, though, I think, is that harder problems, they often require pushing towards boundary cases, deepening that understanding, and the difficulty becomes something that the students start to grapple with themselves. So rather than us just thinking this will be hard or this will be easy, it's relative. Difficulty in maths is relative. Something that a student finds hard, I might find easy, and vice versa. And so that's important that they start to reason with this idea of difficulty. So here's a few that you could try. Give me an example of one easy and one hard example of a calculation which has the answer of 7. So all students can engage with this. Might just be 6 plus 1, or we might go into divisions, square roots, decimals. There's so much if we go to the other extreme. Same thing here. 2 numbers with a difference of 2. Well, it might just be 5 minus 3. But what if we brought in negatives? What if we brought in fractions? Decimals again in here. 2-digit subtraction that's easy, and one that's hard. Well, maybe one involves exchanging, one doesn't perhaps. Ordering some fractions. Well, some fractions are much easier to order than others, as we know. Completing a sequence, so really getting students to think, what's an easy sequence? Maybe 1, 2, 3, 4, 5, and then what's a harder sequence? And maybe it's got fractions in it itself, or maybe it's decreasing sequence, maybe some decimals, negatives in there. Even finding a time difference between 2 times. All students can give you an easy example, and they'll produce a hard example relative to their definition of what does hard mean in this example, in this context. One thing that might be important, because student-generated examples can be really powerful, but often students try and make the most contrived thing ever, with loads of different parts, and they just can't possibly answer it themselves. So I think an important kind of caveat on this is that the students should still always be able to answer the questions themselves rather than just come up with some sort of nonsense that's just really complicated for the sake of being complicated. But anyway, that is the end of this session, and I hope that even if we've sort of revisited a few techniques that you've met in the past, I hope it's given you some ideas that you can maybe try when you're working with your students in your classroom. Think about the general sort of strategies and the principles that are underpinning these strategies, and then think about your kind of curricular area. And it'd be great if you take one of these ideas and just try it in your context, maybe refine it, and then sort of bring that into your practice a bit more. Anyway, my name is Stuart Welsh. As I said at the beginning, if you ever want to get in touch, find out more about the work that we do at ALTA, maybe hear about our Story of Maths curriculum, then you're very welcome to reach out to me, Stuart at alta-education.com. Thanks for listening. Bye now.